Okay, a bit further in our journey on differential equations, and we're looking at two classic applications to explain certain phenomena that use the solutions to differential equations. Newton's law of cooling first, and the logistic function. A professor who resided in Australia, whose name was Professor Julius Sumner Miller, posed this great question. And perhaps he wasn't the initial creator of it, but he told it really well. And you've made a cup of coffee, you can read it there, and the doorbell rings to ensure that you've got that hottest cup of coffee. So it's a cold day, right? You want a hot coffee. To ensure you have the hottest cup of coffee when you return, do you add the milk before answering the door, or do you add the milk afterwards? Okay, which one's going to give us the warmer cup? We know once the milk's added, there'll be an immediate drop in temperature. But did you know that, and it's there on the side, the rate at which a body cools is proportional to the difference between its temperature and the temperature of its immediate surroundings. So the cup of coffee basically cools quicker when the difference between the coffee's temperature is quite a bit different to the temperature, or quite a bit above the temperature of the surroundings. So the scenario is not as simple as it might first appear. We have just a sample. Now this is not conclusive, this is just one experiment. I've seen all sorts of results. I've done experiments with this, or supervised students doing experiments with this, and you can get all different results because there's a lot of factors, but it is fascinating. So if you look, these are fairly thin lines, but if you look at the red graph, that's the milk first, the blue graph is the milk later, and no milk is like the control. And so the no milk, the green one, it cools in sort of an exponential manner, it feels. So as the minutes tick by, it's actually cooling a little bit more quickly up here compared to down here. And you need probably a longer scale to see the effect even more so. Still, if you take a close look, the gradients up here are steeper negative gradients than the ones down here. And so as the coffee gets closer to the ambient temperature, which might be perhaps around 20 degrees, it depends, and the closer it gets, the slower it cools. So when you put milk in early, if you think, oh, I'm going to put my milk in, ding dong, the doorbell must have rung around about here, you get a plummet in temperature. There's the cold milk getting added in, and then it's closer, immediately closer to the temperature of the surroundings. So it's really dropped quick. It's lost, what would that be, 15 degrees, depending, I've drawn all over it, but let's say it's 15 degrees immediately, and then it cools slower from there. Whereas if you put the milk in after you've answered the door, now this is based on a lot of assumptions, of course. Let's say, well, there's somebody was very talkative at the door. Won't say who that might be, but after say 17 minutes or something like that, then the plunge happens. But all the while, this got off to a head start, as it were, but this is cooled quicker. Okay, so I'm not saying that's always the solution, that you'll get a warmer cup, but they're the factors involved in it. So I'm not going to teach a formula necessarily with Newton's law of cooling, although it is possible to use a formula. But I guess I value the reasoning more. As long as you understand Newton's law of cooling, you can derive this formula, or a generic formula, a bit like this one here. So if we're given a question or a task here, body that's at 80 degrees is placed in a room that's kept at a constant temperature, and it's climate controlled at 20 degrees. After 20 minutes, the temperature of that body, it might be a cup of coffee, right, is 60 degrees. Assuming Newton's law of cooling, all right, find the temperature after a further 20 minutes, all right? So it's already gone 20 and then a further 20. And what we need to realize is that the rate of change of temperature is proportional to the difference. Okay, now we've got a negative there because it is cooling, the temperature is dropping, and the rate is dropping, rate of cooling is dropping as the temperature is dropping because it's approaching the ambient temperature, which is 20 degrees, the temperature of the immediate surroundings. So you can see that we have some factor which has got a negative in front of it, multiplied by the difference in the current temperature T. So T is the temperature at any given time. So T, big T of little t. Okay, so temperature depends on the time. Temperature is a function of time. The gap between the temperature at any time and the surrounding temperature. So if that room was 15, that 20 would be a 15. Okay, so we have a differential equation there. So if we have to find the temperature at a further 20 minutes, we're looking for capital T. And this is where we can solve the differential equation, first of all. So whether we're using separation of variables or inversion, we use our usual processes. So we have dt equals dt over t minus 20 equals negative k dt, and we can integrate both sides. One side in terms of capital T, the other in terms of lowercase t. So using our normal processes, we get log modulus t minus 20, and on the right hand side we get negative kt. I'm going to bundle the constant all onto one side, as we've seen before. Now since t is greater than 20, we really just have log of t minus 20. When I say log, I mean natural log in this case, equals the same thing. So we can drop the modulus sign because we know that we've just got positive only there. Okay, and it's natural log. Take natural log positive things. So then writing both sides in exponential form to undo the natural log, as it were, we've got e to the negative kt plus c. Okay, and then we can use index law number 1, write it as a product. Let capital A, just some arbitrary parameter, equal e to the c. So therefore t minus 20, therefore t minus 20 equals a e to the negative kt. So therefore t equals a e to the negative kt plus 20. Now we have two parameters we need to establish, k and a, and therefore we need 2 bits of data, and we do have that. We have 2 times when the temperature was recorded. We need those 2 for this sort of problem. First one we can use is when t equals 0, that's time 0 minutes, temperature is 80 degrees, and so we can sub that in there to that equation at that point and get one of the parameters. And we've got a. Now we've got e to the 0, which is 1, so that's basically a plus 20. So 8 equals a plus 20, so a equals 60, so that helps. Therefore we've got t equals 60 e to the negative kt plus 20. We just need to chase down k. Alright, now we know another bit of data is when t equals 20 minutes, t, the temperature, equals 60 degrees Celsius. So we apply that. So we have 60 equals 60 e to the negative 60 times e to the negative k times 20. I just wrote negative 20k plus 20. And we've got 40. We can separate that down to 2/3, and we've got 2/3 is e to the negative 20k, and take logs both sides. Log of 2/3 equals negative 20k, and so using our calculator, you can stick with exact values if you like. It's probably slightly better than what I'm doing, but I know my answer gives me the spot on answer. So at least 4 decimal places, or if you're a purist, I don't blame you one bit, stick with the exact values. But I get to 4 decimal places, and I wouldn't skimp on that too much. K is 0.0203. So therefore, T equals 60 e to the 0.0203 t plus 20. That's the full version of the equation. Now the question said at after 40, after another 20, right? So that means when t is 40, because there was an initial 20 and then the next 20. So what we're doing is subbing in, scroll back and reread the question if you've forgotten after all this, but what we're doing is that, subbing in 40 for t plus 20, and I get 46 and 2/3 degrees, okay, or 46.6 recurring. The second of two applications is called the logistic equation, or a logistic function. Population's often modeled with this sort of function. It's very often associated with population. And if we have population P versus time T, which might be millions or thousands versus years or months, we have two different curves there. This one here is a typical exponential. Okay, just gets steeper and steeper and steeper. This one here that looks like it sort of starts, along with the exponential, doesn't it? And then it's flattening out into some value k. All right, that's a logistic equation, or a logistic function. K is what's called a carrying capacity, and it's the real or theoretical limits of the resources of an environment. So it might be food, water, space, and whatever else, okay, depending on what we're modeling. Okay, and it will grow pretty quickly, and it'll hit its maximum growth rate, and then it'll flatten out. So vaguely like an S curve. Whoops, that's not a very good one. So all right, that's a little bit better. So it's exponential, or like an exponential, but then it flattens out, and theoretically it's asymptotic to that carrying capacity line. That's mathematically. The real world, of course, has lots of factors, but it's a good model for a lot of things. It sometimes shows up the limitations of continually modeling something exponentially, because things do run out of resources, and the growth rate does slow in some models due to that. So that's a logistic situation versus exponential. An example to illustrate: a population grows according to the differential equation given there, dp dt, p population, t time. It's given to you, and the population goes between 0 and 1,000. So we've got population at time t, and we're given an initial population of 20 of whatever these things are. We've got to do three things: find the population p at t, so the function. We have to find the solution to this differential equation, and then we have to sketch it and find the population p when the growth rate is at a maximum, and that will give us a general conclusion we can come to. 0.025 is 1/40th, and we write that out as such. So that would equal 1/40th p if we expand it, minus p squared over 40,000. Or p on 40 minus p squared over 40,000, and rearranging, just want to get it as a common denominator there, which would be 40,000. We have 1,000 p minus p squared all over 40,000. Take a factor of p out. P outside of 1,000 minus p over 40,000. It's a p, sorry about that. So that's what dp dt equals, and separation of variables there. So solving the differential equation as such, and we have dt over 40,000. Take the integrals of both sides. On the left side we're going to need to use partial fractions. I'm not going to show the full process because that's from another video, but the partials will follow that process. Once you follow it through, you'll get a equals b equals 1 on 1,000. So both a and b are 1 on 1,000. So writing that out fully. Now we've got, it'd be silly to expand all that. So in taking a factor of 1,000 out, that makes it a lot nicer. And we've got that there, dp. I've already taken the factor of 40,000 out on the right hand side, which will make that nice too. Soon I'm going to change that 1,000 minus p to negative p plus 1,000. You'll be ready for that. Multiplying both sides by 40,000, we get 40 outside of the integral of 1 on p dp plus the integral of 1 on 1,000 minus p dp equals the integral of 1 dt, which is just going to be a t. And taking the integration now, we've got natural log of p inside the brackets, 40 outside the natural log of p minus, remember this p is negative, so if you go back to when we integrated that, this will have to be a negative on the top, meaning a negative outside, so that actually will be minus natural log 1,000 minus p equals t. I'm going to bundle the constants all on one side. Now because we have a range there for population well defined, we don't need to worry about the modular signs anymore. Okay, and I'm going to divide both sides by 40 as well and apply log law 2. So that'll come in as this. So log of p over 1,000 minus p equals t plus c. Writing both sides in exponential form, so you have p over 1,000 minus p equals e to the t plus c. Oh, wait, I don't my 40. I said it, but I didn't write it there now because I divided both sides by 40. And so that will be 1 over 40 outside of t plus c there, which using index law 1 is 1/40th, or t over 40 times e, so e to the t over 40 plus e to the c over 40, which is a constant. So we'll call that a e to the t on 40, where a equals e to the c on 40. They're all constants, right? Okay, so we've got p over 1,000 minus p equals a e to the t on 40. So we use some of the provided information. So when t equals 0, p equals 20, the initial values. So if we put that in, we get 20 over 980. That'll equal a. So a equals 1 on 49. Okay, and so we can update that. So we've got p over 1,000 minus p equals 1/49th e to the t over 40. Rearranging now, we've got 1/49 times e to the t over 40 times 1000 minus p. So multiplying both sides by 49, 49p equals e, that's an e to the t over 40, 1000 minus p. So expanding that, so that equals, that should be 1000 e to the t over 40 minus p e to the t on 40. I'm trying to get an expression with p, remember? So I need to get the p's on both sides. That's why I expanded that. So on this side we have 49p plus that term there now. So p e to the t over 40, alright, equals 1000 e to the t on 40. Alright, we can take a factor of p outside of that. I hope you're paying attention. This is a good strategy, even though it is big. And lastly, what we do here is to divide through, so we get p isolated. So we have 1000 e to the t over 40 over 49 plus e to the t over 40. So that's p of t. We can see our population versus time graph. That's what we had to do next, and you can see as it's hitting 1000, that's the carrying capacity there, and we'll summarize that in a minute. Here we can see that it hits a maximum rate of growth and then starts to flatten out there, and that's that classic logistic shape. We had to find the population P when it has its greatest rate of growth. Now, carrying capacity ended up being 1000 because it's asymptotic to 1000. If we use the function and then we take the maximum rate of growth, so we're finding a maximum of this function here. So if we take the derivative and apply the chain rule, we can show that the maximum rate of growth happens at p equals 500, which is half of the carrying capacity. Okay, that's not important, the derivation of that result, but as a fact, p equals 500 is significant. So that's optional, that part there. That's not completely important for our course, but that finding is that p, which is half the carrying capacity, is where the greatest rate of growth, the maximum rate of growth, occurs. So in conclusion, we've looked at two applications of differential equations. In regards to logistic functions, you'll see them expressed in many different ways. There's just some examples there. So the differential equation and the solution to the differential equation with the all-important solution, which is what we plot the logistic function based on. In general, in closing, for the logistic function, we have the following here. So usually that's a given in the questions we're doing. It's not something to memorize necessarily, but be aware that that's the general form of it. Okay, the population is at any time between 0 and the carrying capacity. We have K being the carrying capacity in this model, R is the growth parameter. It's related to how the population grows. Again, that gets given. When we solve it, again, don't memorize that, but usually it's in one of these two forms. Okay, and the carrying capacity is the upper limit on the population. The rate of increase of this approaches, or the rate of increase of the population approaches 0 as the population approaches the carrying capacity, and the population P approaches K as T approaches infinity. Okay, so it's asymptotic. in a sense, and the maximum rate of increase happens when we got half the carrying capacity.